principle. Okay, so let's suppose that cardinality of B is less than the cardinality of A, and A and B are finite and non-empty. If F so A is the bigger set, right? And it's strictly bigger. So if F is a function from A to B, well, what has to happen according to what we have over here? Our function might not be onto, but it goes on to some subset, right? Its image is some subset, which has even smaller cardinality, right? But since the cardinality of this is larger, what has to happen? You have to get two things going to 1. Okay? So F is not 1-to-1. But what I'm going to do is I'm going to write this out directly. I'm not going to say F is not 1-to-1, which is what this gives us. I'm just going to say what it means to not be 1-to-1, which is what? There exist
some W and X in A.
Some what in?
Some W and X in A is equal to F and W is equal to F.
Yeah, WX null of A such that W equals F of X.
W is not equal to X.
Yes, so put that in there. Okay? So why is this called the pigeonhole principle? Because this is your collection of pigeons, A, and B is your collection of pigeonholes. Okay, and nobody besides pigeons likes to be pigeonholed, okay, but that's what we're going to do. So we have A pigeons, and we have a smaller number of holes than we have pigeons. And we want to put each pigeon into a hole. What this says is that there are going to be two pigeons who are going to be sharing a hole, okay? Now this seems like a completely crazy, simple, uninteresting statement, but it actually has remarkable consequences and is used all the time, for example, in computer science and related areas, right? And these arguments can be extremely tricky, okay? But the idea is you have to figure out what your function is, right? What are your pigeons and what are your pigeonholes, right? And how to interpret the non-one-to-oneness of this function, okay? Again, seeing this now, this is completely obvious. If you've got more pigeons than holes, then you're going to have to put two into one hole, okay? But the proofs of this, mainly resulting from here. And actually, in fact, can anybody think about how, given the homework that we've done recently, how this thing here might come into proving something about functions between finite sets, this partition? And how would one-to-one come into play with this? When you have a one-to-one function, what is the inverse image of any point? Set containing a point. How many elements are in it? At most one, right? And so what a one-to-one function does is it partitions the domain into sets that contain exactly one element, okay? And so then you can apply arguments there. All right? So again, if you're interested in this, by all means read it, but otherwise, I think it's best just to understand where these kinds of ideas come from. Okay, so those are the most important things that you will ever need to know in most cases, probably almost everybody, about finiteness. And all the rest is just, trickery using the pigeonhole principle, counting arguments, that kind of thing. But these are the basic theorems that you need to do all that stuff. All right, let's talk about infinite sets. So, a set A is infinite if A is not finite. Okay, great. So, what's your favorite infinite set? Okay, what's your most basic infinite set? Real numbers, I would say. Natural numbers, yeah, real numbers are also infinite. In fact, we'll get into that in a little bit. But natural numbers are the simplest infinite thing, okay? So, and why is that true? Right, so n is infinite. Okay, so why is n infinite? How could you use this, for example, to show that
You can always add one.
You can always add one.
can anybody think of a, well, I mean, but in terms of this, okay, I know you can always add one and all that, but that's not connected to our definition, right? So why is the set of natural numbers going to be infinite according to this?
There are lots of functions from n to n that aren't, that are one-to-one or onto.
For example, okay, so she says, so this tells us that if something is finite, then a function, if these sets are finite, then the function is 1, 1, if and only if it's onto. Okay, well, let's just take a function from n to n, right? N has the same cardinality as itself, right? The identity function is a bijection, right? We went through that already, right? So if it were finite, we wouldn't be able to find a function that's 1 to 1 but not onto. So Estonia, got an example? You said there are lots of them. Well, let's try. 1, 2, 3, 4, 5. Okay, so how about a function that goes back into the natural numbers but is not onto? 1 to 1 but not onto. So where could we? How does it multiply by 2? Okay. Okay, this function, so n goes to 2n, is 1 to 1. You can check that very easily, right? It's an easy function to check. In fact, it's restriction of a linear function, right, which you know is 1 to 1, okay? But not onto. So n is infinite. Okay? That proves it right away.
So you just need one example of a function that proves it.
Yep, because this is a for all statement, right? If A and B are finite sets and f is a function, okay? That's an if-then statement, right? It refers to all possible functions. That they are 1 to 1 if and only if they are onto. So if you're going to show something is infinite, all you got to do is exhibit a single function from the set to itself, right? Because it has the same cardinality as itself. Set to itself that is one of those but not the other. I mean, you could also do, I mean, how could you do, you could also do an onto function, right? That's not 1 to 1. Just take 1 to 1, 2 to 1, and then shift everything back by 1 for the rest, okay? The point is that when you have an infinite set, you have room to maneuver, okay? And this, you've seen this probably already. Well, no, you haven't really. No, I was going to say you might see this in terms of infinite series, that you have room to rearrange things and so on, but I guess you wouldn't really see that till advanced calculus. Okay. All right, so everybody agrees that since we are able to find one function that is 1 to 1 but not onto, that n cannot be finite. Okay, so that gives us a new definition. If A is a set with the same cardinality as n, then A is said to be countably infinite. Okay, I mean, you see why that's probably why that term is used, right? Because if you're in, so remember, having the same cardinality means you have a bijection, okay, between the natural numbers and your set, okay? So whatever 1 goes to, right, whatever 2 goes to, whatever 3 goes to, these are, you can interpret this bijection as being a way of counting all the elements. And so it's 1 to 1, which means, again, you're not having 2 third elements in there, and it's onto, meaning you're counting everything. Okay, so that's countably infinite. Let's look at some examples of other countably infinite sets. Okay, so Z. All right, and so I'm just going to, you can write down the formula for this, okay, but I'm just going to write down with arrows a bijection between N and Z. Okay, we've only got black, so, all right, so I could start anywhere, right, but I'm just going to assign 1 to 0, and then I'm going to go ahead and assign 2 to 1. Now I need to be going in both directions, right, to get everything, so I need to then cross over, and I'll assign 3 to that, and then to make sure I get everything, I'm just going to alternate. So I'll take 4 to here, and then 5, I'll go over to -2, and so on.
Should 4 go to 2?
Oops. Yes. It's going straight down, but of course we're going to be slanted more and more. Okay. Yes. 5%. And 6 goes to 3. Okay? So you can actually write this down. It's not too hard, right? So for example, if it's even, right, where you're going?
To the positive.
You're going to half of it, right? Okay. Proof by picture. Okay, you don't get to get away with that very often, and certainly I don't, but you can write down the formula for that. So Z is countably infinite. Okay, what about Q? That's a little bit more tricky. Okay, there are various issues involved with showing that Q is countably infinite. I mean, part of the problem is that, you know, you can't just look at some fractional form and do some trickery with that, right? Because that's also 1/2, and so you may get into trouble with double counting, right? Okay, so the best way to handle this one, or one way to handle it, is to write, well, there are various theorems about if you're a subset of a countably infinite set, then you're countably infinite or finite, and you can, there's also a theorem that says if you take a countable union, if you take a countable set of sets, and they're all countable, then the union of all those is countably infinite, okay? So it's a little bit harder to show for Q, but it is countably infinite. And again, you can see proof of this in the text if you're interested. Okay, but the important thing is that the set I of irrationals is uncountably infinite. And the proof is amazingly simple if you're willing to believe certain things about decimal expansions. So this is a theorem, Cantor. And involves a method called diagonal proof. So you can do something like this with Q as well, right, to show it's countably infinite, but this one actually shows that it's uncountably infinite. Okay, so here's the idea. You have to be a little careful, and I won't go into the details again. You can see them in the text, but it's pretty straightforward. Okay, so we're going to do a proof by contradiction. Okay, so let's suppose, oh, and also we're just going to look at check that the set of irrationals intersected with 0, 1 is uncountable. That makes it a little easier with the decimal. So if the irrationals contain an uncountable set, if a set contains an uncountable set, then the set itself is also uncountable. This is basically